In this video, we're going to investigate the relationship between similar triangles. Consider the following two similar right triangles. Triangle A has a hypotenuse that is 2 inches long, a base that is the square root of 3 inches long, a lower left angle that is 30 degrees, and a right angle. In triangle B, we only know that the base is the square root of 6.75 inches long, that its lower left angle is 30 degrees, and that it also has a right angle. Before we start finding the lengths of the missing sides of these two different triangles, we're going to talk about what it means for two triangles to be similar. So the first thing to recognize with these two triangles is that they both have a lower left angle that is 30 degrees, and they have a lower right angle that is 90 degrees. Because the sum of all the angles of any triangle must add up to make 180 degrees, if we take that 180 degrees and subtract away the 90 degrees that is the bottom right angle, and the 30 degrees that is the bottom left angle, we can calculate that the top right angle is 60 degrees. But that 60-degree angle is the same for both triangles, because both triangles have the same measurements for the other angles. What it means for two triangles to be called similar is that they are effectively the same shape, that their proportion of the lengths of their sides is consistent from one triangle to the other. Another way to say that is, one is a slightly smaller version than the other. To state this more formally, let's give these missing side lengths letters. So for triangle A, we have a hypotenuse that's 2 inches, a base that is the square root of 3 inches, and so I'll call the missing other leg, the height of it, A. On triangle B, we don't know the length of the hypotenuse, so I will call that H. We do know the base is the square root of 6.75 inches, but we don't know its height, so I will call that height B. Just to point out, I am using lowercase letters for the lengths to not confuse that with the name of the triangle with the capital A and the capital B. What it means for these triangles to be similar is that the ratio of any two side lengths for corresponding sides between the two triangles must be the same. So, in other words, if I take the length of the base of triangle A and compare that to the length of the base of triangle B, that ratio will match the other comparisons that are possible. So, the square root of 3 compared to the square root of 6.75, that ratio will be the same as when we compare the hypotenuse from each triangle. So square root of 3 over the square root of 6.5 will equal 2 over h. And similarly, this will equal also the ratio of the heights of the triangles, A compared to B, or A over B. This is no different than when you look at a city map, and the map says 1 inch on the map is equivalent to 5 miles in the real city. That is another form of similarity. In that case, the ratio of 1 inch compared to 5 miles would be the same ratio, no matter how many inches you're looking at on the map or how many miles you're comparing in the city. In part A, we need to find the length of the hypotenuse of triangle B. Now, while I did draw h on the hypotenuse for triangle B, I'm going to more formally state it here, that h represents the length of the hypotenuse of triangle B, and I will note that that will be in inches. Using just a part of that proportion that we've already set up, I'm going to use that first half, that the square root of 3 compared to the square root of 6.5 will equal the comparison of 2 to h. To solve this equation for h, I will clear fractions by multiplying both sides of the equation by h and by the square root of 6.75. When we multiply h times the square root of 6.75 by both sides, on the right side the h's will cancel. On the left side, the square roots of 6.75 will cancel. So this will leave us with the equation h times the square root of 3 equals 2 times the square root of 6.75. To solve that equation for h, we'll divide both sides by the square root of 3. And when we divide both sides by the square root of 3 and put that 2 times the square root of 6.75 divided by the square root of 3 into our calculator, the answer is 3. So to state our conclusion as a sentence, the length of triangle B's hypotenuse is 3 inches. In part B, we need to find the length of the second leg of triangle A. Well, looking at the proportions and the ratios that we have set up, to find the length of the second leg of triangle A, which is that lowercase a, you'll notice that our equation would require us to know the length of B. Since we know neither of those two sides, these ratios and proportions, the similarity, is not going to help us find the length of the second leg of triangle A. So we'll have to approach this in a slightly different way. I could use the fact that this is a right triangle and use the Pythagorean theorem. To approach it from the Pythagorean theorem, I will first define that A is the length of the second leg of triangle A. Again, making note that this will be measured in inches. Well, the Pythagorean theorem tells us that a squared plus b squared equals c squared, where c squared is the length of the hypotenuse. Well, applying that in this particular situation, we will have a squared plus the square root of 3 squared equals 2 squared. To solve that equation, I'll first square the square root of 3 and I'll square 2. That will become a squared plus 3 equals 4. To solve that for a, we'll first subtract 3 from both sides, so we'll get a squared equals 1. And to finish solving that, recognizing that we're going to use the square root property, if a squared equals 1, then a either equals 1 or a equals negative 1. Since we are dealing with the lengths of sides of triangles, that negative 1 value simply does not make sense in context, so we can ignore it. And we now know the length of the height, or the second leg of triangle A. We'll conclude with a sentence. The length of the second leg of triangle A is 1 inch. And now knowing that the length of A is 1, and having the lengths of all three sides of triangle A, we can answer the final question. Find the length of the second leg of triangle B. We had formally represented that in the picture with that lowercase b, so now we will formally define that. Let little b represent the height of triangle B. Again, this is going to be measured in inches. And now we can go back to the ratios and the proportions that we had been working with. Again, we have that initial comparison of square root of 3 to the square root of 6.75. On the other hand, the comparison that we established in part A was that 2 inches to 3 inches is also the same ratio. So to avoid dealing with square roots, I will use that ratio. So we have 2 inches for the hypotenuse of triangle A compared to 3 inches for the hypotenuse of triangle B must equal the ratio of the two corresponding sides of those two heights. In triangle A, the height is 1, and in triangle B, the height is b. To solve this equation, we can multiply both sides by b and by 3 to cancel out both fractions. Again, the reason we're multiplying both those values, on the right side the b's will cancel out, on the left side the 3's will cancel out. So this gives us the equation 2b equals 3. To solve this for b, we will divide both sides by 2, and b will equal 3/2. The other option is we could write this as a decimal. Since 3 divided by 2 is equal to 1.5 and there's no rounding, I could also say 1.5. And to state our conclusion as a sentence, the length of the second leg of triangle B is 1.5 inches.